Welcome to Linear Algebra Mathematics Modeling session for today. As of these sessions, we'll focus on determinants, how to compute them, interpret their values, and apply them to a real-life example. Let's proceed to our objective. Here are our main objective. We will define what our determinant is for a square matrices, for example 2 times 2, and goes on. That means we'll state exactly what a determinant means for any example n times n matrix is beginning with 2 times 2. Next, we will learn method to compute determinants, a direct formula for 2 times 2, cofactor expansions for 3 times 3 and higher, row reduction for larger matrices. We will cover for each these computation methods in the next turn. Next, we will interpret determinant values for a zero determinant, which means the matrix is non-invertible, and also a non-zero determinant indicates unique inverse and solvable systems. We will see why zero versus non-zero matter for invertibility and solution uniqueness. Finally, we will apply the concept in real-world context to demonstrate these applications. This objective will guide us to the introductions. Determinants are a scalar quantity obtained by a sum of product of the elements of square matrix and their cofactor according to a prescribed rules. In other words, for n times n matrix, there is a rule involving cofactors that yields a single number. The single continues. They help to find the adjoint, inverse of a matrix. Further, to solve the linear equation through matrix inversion method, we need to apply this concept. The cross product of two vectors is remembered easily through the calculation of determinants. This tells us the determinants role in computing inverse and solving systems. For every square matrix of order n times n, a determinant can be defined as scalar value that is real or complex number, where in this case, bracket Cij is a ij element of matrix C. The determinant can be denoted as D or Det, C or C bar. Here our determinant is written by taking the grid of numbers and arranging them inside square bracket. That explains notation why we write C bar or Det C. And finally, if determinant is 0, the matrix is singular. That means it's not invertible. If determinant is 0, the matrix is invertible, which has unique solutions. Let's move on to the next. On this slide, all methodology steps appear together. For this case, let's look on the 2 times 2 matrix first. For 2 times 2 square matrix or matrix of order 2 times 2, we can use the determinant formula to calculate its determinant. The formula is Det square bracket A, B and C, D is equal to A times D minus B times C. And on the right hand side, for any 3 times 3 matrix or square matrix of order 3 times 3 is written as C equals to divide into a column and rows 3 by 3s, A, B, C, A1, B1, C1 and goes on. To find the determinant, start by multiplying a diagonal elements of 2 times 2 matrix and subtracting the products of other diagonal. The slide labels this calculating determinant of 2 times 2 matrix as a Cramer's rule. Calculating determinant of 3 times 3 matrix, we break it down into 2 times 2 parts as mentioned just now, calculating each determinant by factoring the signs and summing them together. So, as illustrated in these presentations, we can see determinant how it's being written, and plus we can see the signs given for us to refer. Examples: A positive, B negative, and C is back to positive. So it's always altering signs each row and each column. Plus, for a larger matrices, we can refer to the visuals that has been presented over here, which is have a trigonal shapes. So we simplify row operation to transform it into triangle form, then multiply the diagonal elements to find the determinants. That refers to row reduction methods. Convert to upper triangle multiple diagonal entries while accounting for any row swap, signs, change or scalings. So we are entering the interesting part of these sessions, which is the real case studies. So over here is a person named Harun. He's a Malaysian fruit exporter. Is optimizing the distributions of his Musang King durian from his orchards to a tree market channel. So over here we can see he trying to export to local wet markets across Penang, Selangor, Johor. Second is export market for international markets, Singapore or Hong Kong. And the third one is online direct to customer. We can use it via e-commerce platform or something like Shopee. So here's the catch. He is challenged how to budget accurately for packaging, transportations and storage costs across these three channels, given different per crate expenses, and how could he ensure the cost of the component behave independently. So we will now create a matrix model to address these challenges following on the next slide. So here is the estimated cost breakdown for his prescribed elements, which is cost for local, international or export market or online, and packaging, transport and storage. So we can see over here it is 20, 35 and 25 for packagings, transportation for local 50, export 100 and online 60, storage 10, export 20 and online 15. Moving on. So we convert the numbers or the value just now into the matrices, which is written C equals to square brackets. Here's are the numbers, and since a shipment vector S is a 3 times 1 column with entries, so the numbers over here are based on the table just now, which is 100 represent the crates to local, 50 represent the crates to exportations, and 200 referring to crates going to online. So here is the step. We take the first row of the matrix, which is 20, 35 and 20, and multiply with the numbers of the S, which is 100, 50 and 200. So here's the calculations. 20 times by the first numbers of the matrix S, which is 100, continues by 35, multiplying with the same number of the S matrix, which is 50, and it goes on with the third numbers of the C matrix, which is 25, and multiply with the numbers of S, which is the 200. Simple calculations, we can get the numbers 8750 for packaging cost. Moving on, we are now about to calculate the transportation cost by multiplying the second row of matrices C, which is 50, 100 and 60, multiplies by the S value, which is 150 and 200. Let's do calculations. First number is 50 times with the first numbers of S, which is hundreds, plus hundreds times by 50, goes on 60 times by 200. So simple calculations, we will get 22,000 only for transportation cost. Next, we will calculate the storage cost. So we're moving on to the third row of matrices C, which is having a values of 10, 20 and 15. Same concept and a bit of calculations, we will get 5,000 in total. So let's do this trick. We will arrange the the values that we calculated earlier for the first, second, and the third rows, and we will sort it, which has been visualized as below. Hi all, without further ado, let's get into next slide, which is determinant. Before we finalizing the budget, we must verify if cost category are independent. If independent, which is C equal to 0, there is a linear independency among row, which is cost categories, or column, which is channels, indicating overlap cost structure, which can complicate budgeting. If determinant C is not equal to 0, the matrix is invertible and the cost categories are independent. We now proceed to calculate determinant C. Let's set up a cofactor determinant C. So over here on the left, you can see we already coordinating the numbers according to rows and columns in the bracket, and going to the right, expansions on the first row and first column. To compute determinant C, we expand along the first row. Denote elements in the row 1, which is 20, 35, and 25. But for this slide, we want to focus on 20 first, which is first row, first column. And the first term is we have to multiply by 20, and determinant 2 times 2 matrix formed by removing the row number 1, column number 1. So for minus 20, the calculation is 100 times 15 minus 60 times 20 equals to 1500 minus 1200, which is equal to 300. Moving on to the next slide. So we see over here we want to expansion on the first row and the second column, whereby we have to select the second numbers on the first row, which is 35. We have to close the first row and the second column. We now try to do matrix multiplication 2 by 2, which is 50 and 10 and 60 and 15. So let's get on to the calculations. So for minus 35, we have to calculate 50 times 15 minus 60 times 10, which is equal to 750 minus 600 and equal to 150. So moving on to the next slide, which is the expansion on the third column. So for this slide, we have to remove the numbers on the first row and the third column to find the 2 times 2 matrix for the remaining numbers, which is 50, 10, and 120. Okay, let's get on to the calculations. For minus 25, we have to do the calculation just as below, which is 50 times 20 minus hundreds times 10, which is equal to 1000 and thousands, and ultimately it will equal to 0. So now we have all the answers for every minor on the first row. So let's get into the final calculations. We have to substitute in two expansions, which is determinant C equal 20, which is the first minor, times 300, the answers from the first 2 times 2 matrix, minus 35. Why minus over here? We have to refer to the methodology, which is we have already given the signs for each row and columns. So back to the calculations, minus 35 times 150, which is the answer for the second minor, plus 25, plus again is the sign from the methodology that we have to refer to, and times by 0, the answers for the third minor. So we have to do the calculation, simple maths, and the answer is 750. That's the answer for determinant C. So as a conclusion, the computed determinant is 750, which is non-zero. Therefore, the cost matrix C is invertible. This confirms that the packaging, transport, and storage costs are linearly independent across the markets. Harun, which is the character in these questions, has a budgeting model is stable and free of hidden dependency. Let's take example, if determinant C had been 0, it would indicate overlapping or redundant cost factor. It's requiring a review of the cost estimated. By this, it does complete our step-by-step demonstration of computing and interpreting determinants for practical applications in the real case studies. So that's all for today, folks. We will meet again in the next video. Thank you for watching. Have a good day.